There is a limit to what we can see, not because the universe ends there, but because light has not had enough time to reach us. That limit is called the observable universe. And beyond it, there is something. The question is, does the universe actually have an edge? Or are we only seeing a small part of something much larger? Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Over the next 2 hours, we will move through this question carefully and without rush. We will begin by thinking about what we actually mean when we say the word universe, because that word carries more complexity than it first appears. The observable universe and the total universe turn out to be very different things, and that distinction shapes everything that follows. From there, we will explore the boundaries of what astronomers can observe. The cosmic horizon, the ancient light that marks the farthest edge of our view, and what that light is, actually telling us about the conditions of the early cosmos. We will look at how matter organizes itself across the larger scales, through the vast filaments and empty voids that make up the cosmic web, the largest structure in existence. We will consider the shape of space itself, whether it curves, whether it closes back on itself, and what geometry has to say about whether the universe can have an edge at all. We will think about expansion, about dark energy, about why the universe is not only growing but accelerating, and what that acceleration means for the regions of space that are even now slipping permanently beyond our reach. And we will spend time with the deeper questions, the ones that sit at the boundary between physics and philosophy. What lies beyond the observable horizon? Can space be infinite? What does topology tell us about the possible shapes a universe can take? And what does it mean, in the end, to be a thinking presence in a cosmos that exceeds our capacity to fully know it? These are not questions with simple answers. They are questions worth sitting with slowly, turning over gently, the way you might hold a smooth stone in your hand without needing to do anything with it. There is no urgency here. Each idea will have time to settle before we move to the next. If you are lying down, let your body relax into wherever you are. If you are studying or working quietly, allow these ideas to move through your mind at whatever pace feels comfortable. We will take our time with all of it. Let us begin. Chapter 1. What we mean by the universe. Before we can ask whether the universe has an edge, we need to spend some time with the word itself. Universe. It is a word we use freely, casually, almost without thinking. And yet, when examined closely, it turns out to carry a great deal of ambiguity. The question of whether the universe has an edge depends entirely on which universe we are talking about, and that distinction is not merely semantic. It is one of the most important clarifications in all of modern cosmology. In everyday speech, the universe simply means everything. All of space, all of matter, all of energy, all of time. The totality of what exists. That is a reasonable starting point, and for most of human history, it was sufficient. The ancient sky was the whole sky. The stars were fixed points in a sphere surrounding the Earth. The universe was, by definition, everything that could be seen and everything that surrounded it, and it was understood to be finite, ordered, and complete. That picture began to change in the 17th century, when astronomers started to understand that the stars were not points fixed to a rotating sphere, but rather distant suns scattered through an immense and possibly limitless space. The scale of the universe expanded dramatically in imagination, and then again in measurement, and then again and again, until the universe as we understand it today bears almost no resemblance to the one our ancestors observed from their hilltops and plains. Modern cosmology makes a careful and important distinction that the ancient view could not have anticipated. It distinguishes between what is called the observable universe and what might be called the total universe, or simply the universe in its full extent. The observable universe is exactly what the name suggests. It is the region of space from which light has had enough time to reach us since the beginning of time as we know it. The universe is approximately 13.8 billion years old. Light travels at a fixed speed. That means there is a sphere around us, centered on our position in space, beyond which we have received no information whatsoever. Not because there is nothing there, but because the light from those regions has not yet reached us. It is traveling toward us even now, but it has not arrived. The boundary of the observable universe is not a wall or a barrier. It is simply the edge of what we can see. The total universe, on the other hand, refers to everything that exists, including the regions we cannot observe. And here the picture becomes genuinely uncertain. We do not know how large the total universe is. We do not know whether it is finite or infinite. We do not know whether the space beyond our observational horizon looks anything like the space within it. These are open questions, and cosmologists treat them with appropriate care. This distinction matters because the two types of edge these two universes might have are fundamentally different in nature. The edge of the observable universe is a practical boundary, an artifact of light speed and cosmic age. The edge of the total universe, if it exists at all, would be something far stranger and more difficult to conceive. It is worth pausing here to appreciate just how remarkable it is that we can speak meaningfully about these things at all. For most of human history, the universe was a local affair. The stars were near. The Earth was the center of everything. The questions we are exploring tonight would have been literally unthinkable to a medieval scholar, not because of any failing on their part, but because the tools and observations needed to even formulate them did not exist. We are asking questions that became possible only within the last century, and many of them have only become scientifically tractable within the last few decades. The universe we now understand is built from a hierarchy of structures. At the smallest scales relevant to cosmology, we have individual stars. Stars grouped together into galaxies. A typical galaxy contains anywhere from a few 100 million to several trillion stars. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars, and it spans roughly 100,000 light years from one side to the other. That number is almost impossible to hold in mind. A light year is the distance light travels in 1 year, moving at just under 300,000 kilometers per second. 100,000 light years is the width of a city of stars that dwarfs any human scale of measurement. And yet, the Milky Way is just one galaxy among many. The observable universe contains an estimated 2 trillion galaxies. That estimate has shifted upward significantly in recent years as our telescopes have grown more sensitive and our understanding of galaxy formation has improved. 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially hosting planets, each planet sitting in space that is itself expanding in every direction. Galaxies are not distributed randomly through space. They gather into clusters. Clusters gather into superclusters. Our own galaxy belongs to a modest cluster called the local group, which in turn is part of a supercluster called Laniakea. Laniakea spans roughly 500 million light years and contains the mass of approximately 100 million billion suns. It is itself a small feature in the large-scale structure of the universe, one thread in a vast cosmic web. Understanding that structure, the way matter arranges itself across cosmic scales, is essential context for the question we are exploring. Because the universe does not appear to be uniform in the way a smooth, featureless expanse would be. It has texture, it has form, and the nature of that form tells us something important about both the history and the possible future geometry of space. There is one more conceptual layer worth introducing before we move forward, and it concerns the relationship between space and time. In everyday experience, space and time feel like separate things. Space is where things are. Time is when things happen. But in the framework of modern physics, and particularly in Einstein's general theory of relativity, space and time are woven together into a single four-dimensional fabric called space-time. This is not merely a mathematical convenience. It reflects something real about the structure of the universe. What this means for our question is that asking about the edge of the universe is not entirely separable from asking about the beginning of time. The universe as we know it began in a state of extraordinary density and temperature approximately 13.8 billion years ago. Space itself, along with time, emerged from that initial state. There was no before in any meaningful sense, not because something prevented existence before that moment, but because time as a dimension of reality came into being, along with space and matter and energy. The question of what lies beyond the edge of the universe is therefore entangled with the question of what existed before the universe began, and both questions push against the same fundamental limits of physical description. This is worth sitting with for a moment. The universe we inhabit is not simply a very large container holding matter and energy. It is a dynamic structure, one that has a history, a geometry, and possibly an extent that exceeds anything we can observe. The edge question is not asking about a wall in empty space. It is asking about the nature of space itself, about whether space is something that can end, or wrap around, or simply continue without limit in all directions. Those are the questions that will occupy us through the hours ahead. For now, it is enough to have established the basic vocabulary, the observable universe and the total universe, the distinction between a practical horizon and a possible physical boundary, the way space and matter are structured on the larger scales, and the deep connection between the geometry of space and the history of time. We will carry these ideas forward into the next chapter, where we will look more carefully at the observable universe itself, at the nature of its boundary, and at what the light reaching us from its farthest edges is actually telling us about the conditions of the early cosmos. For now, let these thoughts settle. The universe is vast beyond easy comprehension, and we are only at the beginning of our exploration. There is no hurry. The questions have waited billions of years. They will keep a little longer while we rest with them. Chapter 2. The Observable Universe and its Horizon. There is a boundary surrounding us in every direction. It is not a wall, not a surface, not a place where space simply stops. It is something more subtle than that, and in some ways more remarkable. It is the edge of the region from which light has had enough time to reach us since the universe began. We call it the cosmic horizon, or more precisely, the particle horizon. And understanding what it is and what it is not turns out to be one of the most clarifying steps we can take toward answering the question of whether the universe has an edge. To understand the horizon, we need to begin with a number. The universe is approximately 13.8 billion years old. That age is not a guess or an approximation pulled from thin air. It is derived from multiple independent lines of evidence, including the observed rate of cosmic expansion, the ages of the oldest stars, and the detailed properties of the cosmic microwave background, radiation. These lines of evidence converge with remarkable consistency on the same figure, giving cosmologists high confidence in that age estimate. Now, light travels at a fixed speed. In the vacuum of space, that speed is just under 300,000 kilometers per second. It is the fastest that any signal or piece of information can travel, and it has been traveling since the earliest moments of cosmic history. Given that the universe is 13.8 billion years old, one might expect the edge of the observable universe to sit at a distance of 13.8 billion light-years in every direction. That would be the intuitive answer. But the intuitive answer is wrong. And understanding why it is wrong tells us something profound about the nature of the universe we inhabit. The reason the observable universe is larger than 13.8 billion light-years is that space itself has been expanding throughout the history of the cosmos. When a distant object emitted light billions of years ago, that object was much closer to us than it is today. As the light traveled toward us, the space between us and its source continued to stretch. The object moved further away, even as its light made the journey. By the time that light arrives at our telescopes, the object that emitted it is now much farther away than the distance the light has traveled. The light traveled 13.8 billion light-years, but the source of that light is now approximately 46 billion light-years from us. This gives the observable universe a diameter of approximately 93 billion light-years. That figure is one of the most frequently cited numbers in modern cosmology, and it tends to stop people short when they first encounter it. The universe is 13.8 billion years old, and yet the observable portion of it spans 93 billion light-years. The expansion of space is responsible for that apparent discrepancy. The boundary of the observable universe, the particle horizon, is therefore not a fixed feature of space. It is a boundary defined by our particular position in time. An observer living 1 billion years from now will have a slightly larger observable universe than we do, because light from regions currently beyond our horizon will have had more time to reach them. The boundary is expanding, slowly, as time passes, and as light from ever more distant regions completes its journey. Our window onto the cosmos grows incrementally with every passing moment. What lies at the very edge of our observable universe, at the farthest distances our most powerful instruments can probe? The answer is light. Not the light of stars or galaxies as we know them, but a uniform, ancient glow that pervades the entire sky and represents one of the most important discoveries in the history of science. This is the cosmic microwave background radiation. In the very early universe, space was filled with a dense, hot plasma of particles and energy. Matter and radiation were locked together, constantly interacting, in a state of near-perfect uniformity. As the universe expanded and cooled, a moment arrived, approximately 380,000 years after the beginning, when the temperature had dropped enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was opaque. Light could not travel freely because it was constantly being scattered by the dense sea of free charge particles. After that moment, the universe became transparent. Light was free to travel unimpeded through space for the first time. The light released at that moment of transparency has been traveling ever since. It has been stretched by the expansion of space from the wavelengths of visible and infrared light into the much longer wavelengths of microwave radiation. Today, it arrives at our instruments from every direction in the sky with almost perfect uniformity, a faint background glow at a temperature of approximately 2.7 degrees above absolute zero. This is the cosmic microwave background, and it represents the farthest thing we can see. It is the universe as it appeared roughly 380,000 years after its beginning, and it sits at the very limit of our observational horizon. Beyond the cosmic microwave background, our telescopes see nothing, not because space is empty in that direction, but because the universe beyond that distance was opaque when the light we could potentially receive from it was emitted. There is no light from those regions that can reach us, not from that early era. In a sense, the cosmic microwave background is a wall of ancient light, a screen beyond which we have no direct observational access. The features of the cosmic microwave background are not perfectly uniform, however. There are tiny variations in temperature across the sky, fluctuations at the level of about 1 part in 100,000. These fluctuations are not random noise. They are the imprint of quantum fluctuations that existed in the earliest moments of the universe, stretched to cosmic scales by a period of extremely rapid expansion called inflation, which we will return to in a later chapter. The patterns in these fluctuations encode an enormous amount of information about the composition, geometry, and history of the universe, and cosmologists have spent decades extracting that information with ever-increasing precision. The data from observations of the cosmic microwave background, most notably from satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory, have given us our most detailed picture of the early universe and our most precise measurements of its fundamental properties. From these observations, we know that the universe is approximately 13.8 billion years old. We know its overall composition in broad terms. We know the rate at which it is expanding. And we know something about its large-scale geometry that has profound implications for the question of whether it has an edge, a topic we will return to when we explore the shape of space in a later chapter. There is another kind of horizon worth mentioning here, one that is related to the particle horizon, but distinct from it in an important way. It is called the event horizon, and it marks the boundary beyond which we will never receive any information, not merely information we haven't received yet, but information we will never receive under any circumstances. The existence of a cosmic event horizon is a consequence of the accelerating expansion of the universe. If the universe were expanding at a constant rate, or even slowing down, the particle horizon would eventually encompass every point in space given enough time. Every region of the universe would eventually be able to send light to every other region. But the expansion of the universe is not constant, and it is not slowing. It is accelerating. Distant galaxies are moving away from us at increasing speeds, driven by a force or energy we call dark energy. Some galaxies are already receding from us faster than the speed of light, not because they are moving through space faster than light, but because the space between us and them is growing so rapidly that the net effect is a recession speed exceeding light. Light emitted by those galaxies today will never reach us. The space between us will continue to expand faster than the light can cross it. Those galaxies are already beyond our event horizon. We can still see them because we are receiving light they emitted in the past, when they were closer and the expansion was slower. But the light they are emitting right now will never arrive. Over cosmic timescales, those galaxies will fade and redshift into invisibility as the light reaching us from them becomes older and older, the most recent light perpetually failing to complete its journey. This has a somewhat melancholy implication for observers in the very distant future. As billions of years pass, the galaxies currently visible to us beyond the local group will gradually fade from view. The accelerating expansion will carry them beyond the event horizon one by one. A civilization existing trillions of years from now, assuming such a thing were possible, might look out at a universe that appears nearly empty, with only the galaxies of the local group visible in an otherwise dark sky. They would have no way of knowing, from observation alone, that billions of other galaxies once shared their observable universe. The evidence would be gone. For now, however, we inhabit a moment in cosmic history with an extraordinary view. The observable universe is rich with structure, filled with galaxies and clusters, and the faint ancient light of the early cosmos. We are, in a sense, living at an optimal time for cosmological observation, early enough that the evidence of the universe's history is still visible, and late enough that our tools are sophisticated enough to read it. The particle horizon tells us where our observational reach ends. It does not tell us where the universe ends. Beyond that boundary, space continues, filled presumably with matter and energy, structured in ways that may or may not resemble what we can see. Whether that space is finite or infinite, whether it curves back on itself or extends without limit, whether it is uniform in its properties or varies in ways we cannot anticipate. These are questions we will continue to approach from different directions throughout this exploration. For now, the image to carry forward is this. We are sitting at the center of our own observable sphere of space, a sphere roughly 93 billion light-years across, surrounded on all sides by a faint microwave glow that represents the earliest light in the universe. Beyond that glow, space continues. How far it continues, and in what form, is the heart of the question we are asking. Let that image rest quietly in your mind as we move into the next chapter, where we will look at how space organizes itself on the larger scales we can observe, through the cosmic web of voids, filaments, and the vast empty regions that make up so much of the universe's volume. Chapter 3. Voids, Filaments, and the large-scale structure of space. If you could step back far enough from the universe, far enough that entire galaxy clusters became invisible, and only the broadest patterns of matter remained visible, you would see something that looks, at first glance, almost biological. A vast, three-dimensional web of filaments and sheets, threaded through with enormous empty regions, stretching in every direction without apparent center or edge. This structure, which cosmologists call the cosmic web, is the largest organized pattern in the known universe. It spans hundreds of millions of light-years in its individual features, and it extends across the full breadth of the observable cosmos. Understanding it is not merely an exercise in description. The cosmic web is a record of how the universe evolved, a physical archive of the processes that shaped space from its earliest moments to the present day. To understand how this structure came to be, we need to go back to the early universe and to those tiny fluctuations in the cosmic microwave background we mentioned in the previous chapter. The universe, at 380,000 years old, was almost perfectly smooth. Matter was distributed through space with extraordinary uniformity, but not perfect uniformity. There were slight variations in density, regions where matter was very marginally more concentrated than average, and regions where it was very marginally less so. The differences were tiny, on the order of 1 part in 100,000. And yet, those tiny differences were the seeds of everything that followed. Gravity is patient. Over hundreds of millions of years, the slightly denser regions began to attract more matter. As matter flowed toward those regions, the denser areas grew denser still, while the regions that had been slightly below average in density grew emptier. This process is called gravitational collapse, and it operated simultaneously at every scale, from the formation of individual stars to the assembly of galaxies to the slow organization of matter across distances of hundreds of millions of light years. The same basic process, gravity amplifying small differences into large structures, operated at every level of the hierarchy. The result, after billions of years of this gradual accumulation, is the cosmic web we observe today. Matter in the universe is not distributed smoothly or randomly. It has gathered into distinct features that cosmologists have catalogued and studied in increasing detail over the past several decades. The most prominent features of the cosmic web are the filaments. These are long, roughly cylindrical concentrations of matter, stretching across tens or hundreds of millions of light years, along which galaxies and galaxy clusters are strung like beads on a thread. Filaments are the highways of the cosmic web, the structures along which matter flows and along which the densest concentrations of galaxies are found. When we look at maps of the large-scale universe, the filaments are the most visually striking features, drawing the eye with their linear reach through space. Where filaments intersect, matter accumulates in the greatest concentrations of all. These intersection points are called nodes or clusters, and they represent the most massive gravitationally bound structures in the universe. Galaxy clusters at these nodes can contain hundreds or even thousands of individual galaxies, all orbiting within a common gravitational potential filled with superheated gas and threaded with dark matter. The most massive known galaxy clusters contain more mass than 1,000,000 billion suns. They are the largest gravitationally bound objects in existence. Between the filaments and clusters lie the sheets, sometimes called walls, which are flattened structures of moderate density connecting the filaments and enclosing the largest empty regions. One of the most famous of these structures is the Sloan Great Wall, a vast sheet of galaxies identified in survey data and stretching over 1 billion light-years in length. At the time of its discovery, it was considered one of the largest known structures in the universe, though subsequent surveys have identified even larger features, including the Hercules Corona Borealis Great Wall, which spans several billion light-years and pushes against the upper limits of what cosmological models expect to exist. And then there are the voids. These are the regions that occupy the spaces between the filaments and walls, and they are, by volume, the dominant feature of the universe. Voids are not empty in the strict sense. They contain some matter, some galaxies, some gas. But their density is far below the cosmic average, sometimes by a factor of 10 or more compared to the typical density of space. They are the great empty rooms of the universe, the dark, quiet spaces between the glowing threads of the cosmic web. Individual voids range in size from a few tens of millions of light-years across to several 100 million light-years. The Boötes void, discovered in 1981, spans approximately 330 million light-years and contains far fewer galaxies than would be expected for a region of that size. When it was first identified, astronomers found it so improbably empty that it prompted genuine puzzlement. A void that large, that empty, seemed difficult to explain within the models of structure formation then available. Subsequent understanding of how voids grow and merge has made such large empty regions more theoretically tractable. But the Boötes void remains one of the most striking examples of just how unevenly matter is distributed through the cosmos. Voids are not simply passive absences in the cosmic web. They are dynamic structures with their own internal organization and evolution. Matter near the edges of voids is slowly being evacuated, drawn outward toward the surrounding filaments and walls by gravity. The interior of a void is a region of relative gravitational underdensity, which means that matter within it experiences a net outward push relative to the surrounding denser regions. Over cosmic time, voids grow, merge, and reshape the boundaries of the cosmic web around them. The web is not static. It is a slowly evolving structure, its filaments growing denser, its voids growing emptier, its overall texture coarsening as matter continues to accumulate along the gravitational pathways laid down in the early universe. Cosmologists study the cosmic web through large-scale galaxy surveys, projects that map the positions of millions or billions of galaxies across vast volumes of space and reconstruct the three-dimensional distribution of matter from those positions. Projects such as the Sloan Digital Sky Survey, the 2-degree field galaxy redshift survey, and more recently the Dark Energy Spectroscopic Instrument Survey, have produced increasingly detailed maps of the universe out to distances of several billion light-years. These maps reveal the cosmic web in remarkable detail, tracing the filaments and voids with enough resolution to test theoretical models of structure formation and to probe the properties of dark matter and dark energy. One of the most important things these surveys have revealed is that the cosmic web, despite its complex and intricate appearance, is remarkably consistent with the predictions of the standard cosmological model. The sizes of voids, the lengths of filaments, the masses of clusters, and the overall distribution of matter all match what theoretical models, based on the properties of dark matter and the initial fluctuations in the early universe, predict. This consistency is a significant confirmation of our overall understanding of how the universe evolved. It also tells us something relevant to our central question. The cosmic web is statistically homogeneous on the larger scales. That is to say, if you average the distribution of matter over volumes large enough to contain many filaments and many voids, the universe looks roughly the same in every direction and from every position. This property is called isotropy and homogeneity, and together they form what cosmologists call the cosmological principle. The universe, on the very largest scales, has no preferred direction and no preferred location. No point in space is special. No direction is different from any other. This principle is not simply assumed. It is supported by observation. The cosmic microwave background is uniform across the sky to extraordinary precision, indicating that the early universe was highly isotropic. Galaxy surveys show that the distribution of matter, while locally complex, averages out to the same density in every direction when viewed at large enough scales. The cosmic web has a similar texture throughout the observable universe, without any apparent center, without any boundary visible within our observational reach. The cosmological principle has profound implications for the question of edges. If the universe is truly homogeneous and isotropic on the larger scales, then there is no observational evidence for a center, and by extension, no obvious reason to expect an edge in any particular direction. An edge would be a special feature. It would break the symmetry. And everything we observe suggests that the universe, at least within the volume we can see, does not have special features of that kind. This does not prove that the universe is infinite. A finite universe could still be homogeneous if it has the right geometry. a possibility we will explore in detail when we consider the shape of space. But it does mean that the evidence for an edge, or for any preferred structure that would imply an edge, is absent from everything we can currently observe. There is something quietly reassuring about the cosmic web, despite its vast scale and the emptiness of its voids. It speaks to the consistency of physical law across enormous distances. The same gravitational processes that assembled the Milky Way into its spiral form also assembled the superclusters and voids that surround it. The same quantum fluctuations that seeded the first density variations in the early universe grew, over billions of years, into the largest structures in existence. There is a continuous thread of physical causality running from the smallest scales of the early cosmos to the grandest patterns of the present-day universe. When we look out at the cosmic web, we are looking at the cumulative record of 13 billion years of gravitational evolution. The voids are the places matter left behind. The filaments are the paths it traveled. The clusters are the places it gathered most completely. All of it together is a map of how gravity has shaped space. And it is a map that appears to have no edge within the portion of the universe we can observe. In the next chapter, we will take a different approach to the question of extent and edges. Rather than looking at how matter is distributed through space, we will look at the shape of space itself. Because the geometry of the universe, whether it is flat, positively curved, or negatively curved, turns out to have everything to do with whether the universe is finite or infinite, and whether the question of an edge can even be meaningfully asked. Rest here for a moment. The cosmic web is a vast and quiet thing. Its voids are among the most peaceful environments in existence, nearly empty, nearly still, drifting slowly apart as the universe continues its long expansion. There is something fitting about that image as a resting place before we move on. Chapter 4. The shape of space. When we ask whether the universe has an edge, we are asking, at its deepest level, a question about geometry. Not the geometry of objects within space, but the geometry of space itself. This is a distinction that took centuries to become thinkable, and it remains one of the most conceptually demanding aspects of modern cosmology. But it is also one of the most rewarding, because the shape of space, it turns out, determines whether the universe can have an edge at all, and if so, what kind. To approach this carefully, we need to begin with something familiar. Geometry, as most of us first encounter it, is Euclidean. It is the geometry of flat surfaces, of straight lines, of triangles whose interior angles always add up to exactly 180 degrees. In Euclidean geometry, parallel lines never meet. The shortest path between 2 points is a straight line. Circles have a circumference exactly equal to pi times their diameter. These rules feel self-evident, and for most practical purposes on the surface of the Earth and within our immediate surroundings, they are accurate enough to be treated as facts of nature. But they are not universal facts. They are the rules of one particular kind of geometry, the flat kind, and the universe is not obligated to follow them. Einstein's general theory of relativity, developed in the early 20th century, replaced the idea of gravity as a force with the idea of gravity as the curvature of spacetime. Mass and energy bend the fabric of spacetime around them, and what we experience as gravitational attraction is actually the tendency of objects to follow the straightest possible paths through curved spacetime. The geometry of the universe is not fixed and predetermined. It is shaped by the matter and energy within it. This means that the large-scale geometry of the universe, the overall shape of space on the grandest scales, is a physical question with a physical answer. And cosmologists have three broad possibilities to consider. The first possibility is a flat universe. In a flat universe, the rules of Euclidean geometry hold at the larger scales. Parallel lines remain parallel forever. The angles of a triangle drawn across cosmic distances sum to exactly 180 degrees. Space extends in all directions without curving, without bending back on itself. A flat universe can be either finite or infinite in extent, depending on its topology, a subtlety we will return to shortly. But in its geometry, it is the familiar, uncurved space of everyday intuition, simply extended without limit. The second possibility is a positively curved universe. To understand positive curvature, it helps to think about the surface of a sphere. On a sphere, the rules of flat geometry break down. Two lines drawn perpendicular to the equator, which are parallel at the equator itself, will eventually meet at the poles. A triangle drawn on the surface of a sphere has interior angles that sum to more than 180 degrees. The circumference of a circle is less than pi times its diameter. A universe with positive curvature behaves analogously in 3 dimensions. It curves back on itself in a way that is difficult to visualize directly, but which has concrete geometric consequences. Most importantly, a positively curved universe is finite in volume without having an edge. Just as the surface of a sphere has a finite area but no boundary, a positively curved 3-dimensional universe would have a finite volume, but no point at which space simply ends. The third possibility is a negatively curved universe. Negative curvature is perhaps the least intuitive of the 3. A surface of negative curvature resembles a saddle shape, curving away from itself in all directions. In a negatively curved universe, parallel lines diverge rather than converging, and the angles of a triangle sum to less than 180 degrees. A negatively curved universe is generally expected to be infinite in extent, extending outward without limit in all directions. These 3 geometries, flat, positively curved, and negatively curved, correspond in cosmology to 3 possible fates for the universe and 3 possible answers to the question of whether it is finite or infinite. And the determining factor between them is the total density of matter and energy in the universe relative to a critical value called the critical density. If the actual density of the universe exactly equals the critical density, the geometry is flat. If it exceeds the critical density, the geometry is positively curved and the universe is finite. If it falls below the critical density, the geometry is negatively curved and the universe is infinite. The critical density is an extraordinarily specific number, approximately equivalent to about 5 hydrogen atoms per cubic meter of space, averaged across the entire universe. That is a nearly perfect vacuum by any everyday standard, and yet it is a meaningful benchmark in cosmology. So what do the observations tell us? What is the actual measured density of the universe compared to the critical density? The answer, derived primarily from detailed analysis of the cosmic microwave background and from measurements of the large-scale distribution of matter, is that the universe appears to be flat, or very nearly so. The measured density of the universe is within about 1% of the critical density. The geometry of space, as best we can determine from every observational tool at our disposal, is Euclidean on the larger scales. Parallel lines, extended across billions of light years, would remain parallel. Triangles would have angles summing to 180 degrees. This result is simultaneously clarifying and humbling. It is clarifying because it gives us a concrete answer to the geometry question, at least within our observational reach. It is humbling because a flat universe, depending on its topology, is consistent with being infinite in extent, and an infinite universe is one that most certainly has no edge in any conventional sense. But here a subtlety enters the picture, one that is easy to overlook and important not to. The geometry of the universe and the topology of the universe are not the same thing. Geometry describes the local rules of space, how distances are measured, how angles behave, how curvature operates. Topology describes the global shape of space, how it is connected, whether it wraps around on itself, whether there are multiple paths between the same 2 points. A flat universe does not have to be infinite. It is possible for space to be locally flat, obeying Euclidean geometry at every point, and yet globally finite, wrapping around on itself in a way that creates a closed structure. The simplest example of this in 2 dimensions is a torus, the surface of a donut shape. A flat torus is locally flat at every point, meaning a small triangle drawn anywhere on. It has angles summing to exactly 180 degrees. But globally, the torus is finite. It has a finite area, and crucially, it has no edge. If you travel in a straight line on a flat torus, you will eventually return to your starting point without ever encountering a boundary. A 3-dimensional version of this, sometimes called a hypertorus or a 3-torus, is one possible topology for our universe. In such a universe, space would be finite in volume, but completely without edges. If you traveled far enough in any direction, you would eventually return to where you started. Light leaving our galaxy would, after traveling an enormous distance, potentially return from the opposite direction and allow us to see our own galaxy as it appeared in the distant past. Cosmologists have searched for evidence of this kind of topology in the cosmic microwave background and in galaxy surveys. One signature of a finite wraparound universe would be the appearance of matched circles. In the microwave background, pairs of circles in different parts of the sky showing identical patterns of temperature fluctuations, the result of light from the same early universe region reaching us from 2 different directions after having wrapped around the topology of space. So far, no convincing evidence of such matched circles has been found. This does not rule out a finite topology, but it does place constraints on it. If the universe does wrap around on itself, it must do so on a scale larger than our observable horizon, putting the repetition pattern beyond the range of our current instruments. This is a striking conclusion. The universe may be finite in volume, and yet we would have no way of detecting that finitude directly, because the scale on which space repeats itself is larger than the sphere of space from which we can receive any information. We would be living inside a finite but boundless universe, unable to see its global structure because our observational horizon does not reach far enough. There is something deeply interesting about that possibility. It means that the question of whether the universe is finite or infinite may be, in a practical sense, unanswerable by direct observation. The geometry tells us the universe is flat or very nearly so. The topology remains undetermined, and the size of the total universe, whether it is just somewhat larger than our observable region or vastly larger or truly infinite, is a question that current physics cannot resolve. What the shape of space does tell us, with reasonable confidence, is that within our observable region, space shows no signs of curvature significant enough to suggest a nearby edge. The universe we can see is flat, homogeneous, and isotropic. It gives no indication, geometrically, of approaching any kind of boundary. If an edge exists, it lies well beyond the reach of our instruments, in the region of space that the cosmic horizon permanently conceals from our view. As we move into the next chapter, we will turn from the geometry of space to the dynamics of space, to the question of how space is changing over time and what that change implies for the long-term structure of the universe. Expansion, it turns out, is not a simple or uniform process, and the force driving it carries implications that reach far beyond what even Einstein initially anticipated. For now, let the geometry settle. Flat space, extending in all directions, neither curving toward an edge, nor bending back toward a beginning. A universe that looks, from the inside, like it simply goes on. Whether it truly does go on forever, or whether it wraps quietly around itself, just beyond the limit of what we can see, is a question we hold gently, without forcing an answer that the evidence does not yet support. Chapter 5. Expansion, Dark Energy, and the Accelerating Cosmos. There is a common misconception about the expansion of the universe that is worth addressing before anything else. When people first hear that the universe is expanding, they tend to imagine it the way they might imagine an explosion, matter flying outward from a central point into surrounding empty space, the way debris spreads from a detonation. This image is intuitive, but it is wrong in almost every important detail. The universe is not expanding into anything. There is no surrounding empty space waiting to be filled. The expansion of the universe is not the movement of matter through space. It is the stretching of space itself. Every region of space is growing, incrementally, relative to every other region. The distances between galaxies are increasing, not because galaxies are moving through space away from each other, but because the space between them is expanding. This is a distinction that matters enormously for understanding what expansion means and what it implies about edges and extent. A useful analogy, imperfect like all analogies but illuminating nonetheless, is to imagine dots drawn on the surface of a balloon. As the balloon is inflated, each dot moves away from every other dot. No dot is the center of the expansion. No dot is special. From the perspective of any single dot, every other dot is receding, and the farther away a dot is, the faster it appears to recede. This is exactly what we observe when we look at distant galaxies. Every galaxy beyond our local group is moving away from us, and the speed at which it recedes is proportional to its distance. This relationship, known as Hubble's law, was first established observationally by Edwin Hubble in 1929, and it transformed our understanding of the cosmos. Hubble's discovery was made possible by a property of light called redshift. When a source of light moves away from an observer, the wavelengths of the light it emits are stretched, shifting toward the red end of the spectrum. The faster the source recedes, the greater the redshift. By measuring the redshift of light from distant galaxies and comparing it to the expected wavelengths of specific atomic spectral lines, astronomers can determine how fast those galaxies are receding and, combined with independent distance measurements, can map the expansion of the universe across cosmic scales. What Hubble found was that the universe is not static. Galaxies are receding from us in every direction, and the rate of recession increases with distance. This implied that the universe had been smaller in the past, that all the matter we observe had once been compressed into a far smaller volume, and that there must have been a beginning to the current state of expansion. This was the observational foundation on which the Big Bang model was built, and it remains one of the central pillars of modern cosmology. For several decades after Hubble's discovery, the Natural assumption was that the expansion of the universe was slowing down. Gravity, after all, is an attractive force. Every piece of matter in the universe pulls on every other piece. The collective gravitational attraction of all the matter in the universe should act as a brake on the expansion, gradually slowing the rate at which galaxies recede from one another. Depending on how much matter the universe contained, this braking effect might eventually halt the expansion and reverse it, leading to a future contraction called the Big Crunch, or it might slow the expansion without ever stopping it, allowing the universe to continue growing forever, but at a diminishing rate. In 1998, two independent research teams studying a specific type of stellar explosion called a Type 1a supernova discovered something that overturned this expectation entirely. Type 1a supernova are useful to cosmologists because they all explode with approximately the same intrinsic brightness, making them reliable distance markers across cosmic scales. By comparing how bright these supernovae appeared in the sky with how bright they should be based on their distance, as inferred from their redshift, the teams could determine whether the expansion of the universe was slowing, constant, or accelerating. The answer was acceleration. Distant supernovae were fainter than expected, meaning they were farther away than the expansion rate at the time of their explosion would have predicted. The universe was not slowing down. It was speeding up. The rate of expansion was increasing. This discovery earned its lead researchers the Nobel Prize in Physics in 2011, and it introduced into cosmology a profound and still poorly understood quantity that we call dark energy. Dark energy is the name given to whatever is driving the accelerating expansion. It is not dark in the sense of being hidden or sinister. The word dark in this context simply means that it does not interact with light and cannot be directly observed through electromagnetic radiation. What we know about dark energy comes entirely from its effects on the large-scale dynamics of the universe. And what those effects tell us is that dark energy acts as a kind of repulsive pressure, pushing space apart rather than pulling it together, and doing so with a strength that increases as the universe grows. The leading theoretical candidate for dark energy is something called the cosmological constant, a term that Einstein himself introduced into his field equations in 1917, ironically for the wrong reason. Einstein added the cosmological constant to his equations to make them describe a static universe, because the prevailing assumption of his era was that the universe was eternal and unchanging. When Hubble's observations established that the universe was expanding, Einstein reportedly described the cosmological constant as his greatest blunder and abandoned it. Decades later, the discovery of accelerating expansion brought it back, this time as a potential explanation for the force driving that acceleration. In its modern interpretation, the cosmological constant represents the energy density of empty space itself, sometimes called vacuum energy. Empty space, in the framework of quantum field theory, is not truly empty. It is filled with quantum fields that fluctuate constantly, and those fluctuations carry energy. If empty space has a positive energy density, then as the universe expands and more space comes into existence, the total amount of dark energy increases proportionally. This creates a self-reinforcing dynamic. More space means more dark energy, which drives faster expansion, which creates more space. The precise value of the cosmological constant, as measured from supernova observations and confirmed by other methods, is extraordinarily small. It is so small that it has no measurable effect on scales smaller than galaxy clusters, on human scales, on planetary scales, even on the scales of individual galaxies. dark energy is negligible compared to gravity. But on the scales of hundreds of millions and billions of light years, it dominates. It is the largest single contribution to the energy budget of the universe, accounting for approximately 68% of the total energy density of the cosmos. Dark matter accounts for about 27%, and ordinary matter, everything made of atoms, everything we can directly observe, accounts for only about 5%. The implications of dark energy for the long-term future of the universe are significant. If the acceleration continues, and current observations give no indication that it will stop, then the universe will continue to expand at an ever-increasing rate indefinitely. Galaxies beyond our local group will continue to recede, their light increasingly redshifted, until they fade permanently beyond our event horizon. The observable universe will, over timescales of trillions of years, grow, emptier and darker as the expansion carries everything away. There is a scenario, more speculative but worth mentioning, called the Big Rip. In this scenario, dark energy is not a constant, but a quantity that grows stronger over time, a variant sometimes called phantom energy. If dark energy strengthens sufficiently, the repulsive force it exerts could eventually overcome not just the gravity holding galaxy clusters together, but the gravity holding individual galaxies together, then the forces holding solar systems together, then the electromagnetic forces holding planets and rocks, and eventually atoms together. In the Big Rip scenario, the universe ends not with a crunch or a fade, but with a literal tearing apart of all structure at every scale. Current observations do not strongly support this scenario, and many cosmologists consider it unlikely, but it is a logical consequence of certain models of dark energy and cannot be ruled out with current data. For our central question about edges, the expansion of the universe and the role of dark energy introduce an important new dimension. The expansion does not create an edge, but it does create a boundary, the event horizon, beyond which information can never reach us. That boundary is not fixed. As the expansion accelerates, the event horizon actually shrinks in terms of the region of space it encompasses. Galaxies that are currently within our observational reach, but beyond a certain distance, are already sending us their last communicable light. The messages they will send in the future will never arrive. In this sense, dark energy is slowly but inexorably reducing the effective size of our connected universe, the region of space with which we can ever exchange information. It is not creating an edge in space, but it is creating an ever more confining horizon of causality, a shrinking bubble of cosmic connection within an expanding but increasingly unreachable cosmos. There is something both unsettling and quietly peaceful about this picture. The universe is growing, vast beyond all comprehension, and yet the portion of it we can ever know is not growing with it. We are, in a sense, on an island that is not shrinking, but whose surrounding ocean is expanding faster than any boat could cross. The stars and galaxies within our local group, bound together by gravity strong enough to resist the expansion, will remain with us. Everything else is, on cosmic timescales, already leaving. In the next chapter, we will turn to the regions beyond our horizon directly, to the question of what, if anything, physics can say about the space we will never observe. It is here that the conversation moves from measurement to inference, from observation to theory, and the answers become correspondingly more uncertain and more fascinating. Rest for a moment with the image of an expanding universe, space stretching quietly in every direction, carrying galaxies apart like notes drifting slowly out of hearing. It is a large and unhurried process, and it has been underway for nearly 14 billion years without pause. Chapter 6. What lies beyond the observable edge? There is a region of space that surrounds our observable universe in every direction. A region from which no light has ever reached us, and from which no signal of any kind can arrive in time to be detected by any instrument we could ever build. It is not a void in the sense of being empty, at least not necessarily. It is simply beyond our reach, permanently and by definition, sealed off from us by the combined effects of cosmic age and the speed of light. And yet, it is not beyond the reach of physics. We cannot observe it, but we can reason about it, and what that reasoning reveals is one of the most remarkable and contested frontiers in all of modern science. The first and most conservative thing physics can say about the region beyond our observable horizon is that it is probably more of the same. This inference rests on the cosmological principle we encountered earlier, the observation that the universe appears homogeneous and isotropic on the larger scales. If the laws of physics are the same everywhere, and if the initial conditions of the universe were broadly uniform, then the regions of space beyond our horizon should contain matter and energy distributed in roughly the same way as the matter and energy we can observe. There should be galaxies, clusters, filaments, and voids arranged in a cosmic web, similar to the one we map within our observable sphere. The physics governing those regions should be identical to the physics governing ours. This is not a guaranteed conclusion. It is an inference based on the assumption that the conditions visible to us are representative of conditions beyond our view. That assumption could be wrong, but it is the most parsimonious assumption available, the one that requires the fewest additional hypotheses, and it is broadly consistent with the leading theoretical frameworks for the early universe. If the region beyond our horizon is indeed more of the same, then the total universe is simply larger than the observable universe, perhaps much larger. How much larger is a question that depends on both the geometry and the topology of space, subjects we have already begun to explore. In a flat, infinite universe, the total universe would be infinitely larger than our observable portion. In a flat but finite universe with a compact topology, it would be larger by some finite factor. In either case, our observable sphere would represent a tiny, perhaps negligible, fraction of the whole. Some cosmologists have attempted to place lower bounds on the size of the total universe based on the observed flatness of space and the absence of any detectable topology signal. If the universe wraps around on itself, the scale of that wrapping must be larger than our observable horizon. Otherwise, we would have detected the signature of repeated structures. This places the total universe at a minimum of several times larger than our observable region, and quite possibly vastly larger. Some estimates, based on inflationary theory, suggest the total universe could be larger than our observable portion by a factor so enormous that it defies any useful comparison. This brings us to inflation, a theoretical framework that is central to any serious discussion of what lies beyond our horizon. Inflation is the name given to a proposed period of extraordinarily rapid expansion that is thought to have occurred in the first tiny fraction of a second after the beginning of the universe. During inflation, the universe is thought to have expanded by a factor of at least 10 to the power of 26, and possibly far more, in an interval of time so brief that it makes a billionth of a second seem leisurely by comparison. This expansion was driven not by dark energy as we know it today, but by a different form of energy associated with a hypothetical field called the inflaton field. which briefly dominated the energy budget of the early universe before decaying into the matter and radiation we observe today. Inflation was proposed in the early 1980s, primarily by the physicist Alan Guth, as a solution to several puzzling features of the observed universe that the standard Big Bang model struggled to explain. One of these puzzles was the remarkable uniformity of the cosmic microwave background. If different regions of the early universe had never been in causal contact, had never been close enough together for light or any signal to travel between them, how could they have reached such similar temperatures? Inflation solves this by proposing that all the regions we observe today were once in extremely close contact, packed into a volume far smaller than an atom, before the inflationary expansion stretched them to cosmic scales. Another puzzle was the flatness of space. For the universe to be as flat as we observe it to be today, the initial conditions of the Big Bang would have had to be fine-tuned to an extraordinary degree. A very slight excess of matter in the early universe would have caused it to collapse long ago. A very slight deficit would have caused it to expand so rapidly that no structures would ever have formed. Inflation naturally drives the geometry of the universe toward flatness, because the enormous expansion smooths out any initial curvature, the way inflating a balloon smooths out wrinkles in its surface. Inflation also explains the origin of the small density fluctuations imprinted in the cosmic microwave background. During the inflationary period, quantum fluctuations in the inflaton field were stretched to macroscopic scales. These fluctuations became the seeds of all the large-scale structure in the universe. The variations in density that gravity subsequently amplified into galaxies, clusters, and the cosmic web. The inflationary framework is supported by several lines of observational evidence, most notably the specific pattern of fluctuations in the cosmic microwave background, which matches the predictions of inflationary models with impressive precision. It is not without its critics and its open questions, and different variants of inflationary theory make different predictions that future observations may be able to test. But it is currently the leading framework for understanding the very early universe, and it has profound implications for what lies beyond our observable horizon. One of those implications is the possibility of eternal inflation. In many inflationary models, the process of inflation does not end uniformly everywhere at once. Instead, inflation ends in some regions while continuing in others. The regions where inflation ends form what might be called bubble universes, regions of space that settle into a lower energy state and begin to evolve according to the physics we observe. But the space between those bubbles continues to inflate, expanding faster than the bubbles can merge, so that new bubbles are constantly forming within an ever-expanding inflationary background. This process, once started, may never end. It may be generating new bubble universes continuously, including the one we inhabit, in a vast and possibly eternal inflationary sea. This is the multiverse, or more precisely, one version of it. The term multiverse is used in several different contexts in physics, referring to different theoretical frameworks that all involve the existence of regions of space or space-time beyond our observable universe. The inflationary multiverse, sometimes called the Level 2 multiverse in physicist Max Tegmark's classification, is perhaps the most physically motivated of these frameworks. It emerges directly from the mathematics of inflationary theory without requiring any additional assumptions beyond those already needed to explain what we observe. Within the inflationary multiverse, different bubble universes could, in principle, have different physical properties. The process by which inflation ends in each bubble could result in different values for the fundamental constants of physics, different strengths of the four fundamental forces, different masses for elementary particles. Some bubbles might have physical laws hospitable to the formation of complex structures. Others might collapse immediately or expand too rapidly for matter to clump, or have no chemistry capable of supporting anything resembling life. Our universe, with its particular set of physical constants, would be one bubble among an enormously large or possibly infinite number, distinguished not by any special position in the multiverse, but simply by having conditions compatible with the existence of observers capable of asking about it. This last point connects to a philosophical principle called the anthropic principle, which states in its most basic form that the conditions we observe must be compatible with our existence as observers. It sounds almost trivially true, but it has non-trivial implications in the context of a multiverse. If there are an enormous number of universes with varying physical constants, it is not surprising that we find ourselves in one where the constants happen to support complexity and life. We could not find ourselves anywhere else. The multiverse is deeply controversial, not because it is obviously wrong, but because it sits at the edge of what physics can currently test. If the other bubble universes are forever beyond our observable horizon, as the mathematics of eternal inflation suggests they must be, then we cannot directly detect them. We cannot send signals to them or receive signals from them. They are causally disconnected from us in the most complete sense possible. Some physicists argue that an untestable hypothesis lies outside the domain of science. Others argue that if a theory makes correct predictions about what we can observe, and if the existence of a multiverse is a mathematical consequence of that theory, then the multiverse deserves to be taken seriously as a physical possibility, even if direct confirmation is impossible. There is one tantalizing exception to the general inaccessibility of other bubble universes. If our bubble universe and another bubble universe were close enough in the inflationary landscape, they might have collided in the distant past. Such a collision would have left a distinctive imprint in the cosmic microwave background, a circular pattern of anomalous temperature in one region of the sky. Cosmologists have searched for such patterns in the microwave background data with considerable care. Some researchers have reported candidate signals. Others have argued those signals are consistent with statistical noise. The search continues, and future observations with greater sensitivity may resolve the question. Whether or not the multiverse turns out to be a physically meaningful concept, the discussion it prompts is valuable for our central question. It reminds us that the observable universe, vast as it is, may be a small and perhaps unrepresentative sample of a much larger reality. It reminds us that the edge of what we can see is not necessarily the edge of what exists, and it raises the possibility that the question of whether the universe has an edge may need to be replaced by a more layered question about which universe we are asking, and what we mean by edges in a reality that may be far larger and stranger than any single framework can capture. What lies beyond the observable edge, then, is most likely more space, more matter, more structure, arranged according to the same physical laws that govern everything we can observe. It may be that simple, or it may be that beyond our horizon lies a landscape of varying physics, a foam of bubble universes each with its own character, embedded in an inflationary background that has been expanding since before our own beginning. We cannot know with certainty, but we can hold both possibilities with intellectual honesty, neither dismissing the multiverse as science fiction, nor treating it as established fact, but recognizing it as a serious theoretical possibility that emerges from our best current understanding of the early universe. The universe does not owe us an observable answer to every question we can ask. Some of its secrets may be permanently beyond our reach, sealed behind a horizon that no technology can overcome. That is not a failure of science. It is a feature of the universe we inhabit, and there is something quietly humbling about it. In the next chapter, we will step back from the physical and into the mathematical, exploring what infinity means in the context of space, how topology shapes the possible structures a universe can have, and what it might mean for space to be finite without having a boundary. Take a slow breath here. The questions in this chapter are among the largest that human minds have ever formed, and they deserve to be held gently rather than pressed for quick resolution. The universe beyond our horizon is there, in whatever form it takes, continuing its quiet existence beyond the reach of our instruments and the span of our light. Chapter 7. Infinity, Topology, and the Nature of Space. Of all the concepts that arise in the study of the universe, infinity is perhaps the most resistant to genuine understanding. We use the word freely. We encounter it in mathematics, in philosophy, in casual conversation. And yet, when we try to hold the concept of infinity in our minds as a physical reality, as an actual property of the space we inhabit, something quietly resists. Infinity is not merely a very large number. It is not a number at all. It is a quality, a statement that something continues without end, without limit, without any boundary that could in principle be reached. And whether the universe is infinite in this genuine sense, rather than merely very large, is one of the deepest open questions in cosmology. Let us begin with what mathematics has to say about infinity, because the mathematical treatment is more nuanced than everyday intuition suggests, and that nuance turns out to matter for cosmology. In thus mathematics, there is not one infinity, but many. The mathematician Georg Cantor, working in the late 19th century, developed a rigorous framework for comparing infinite sets and demonstrated that some infinities are larger than others. The set of all whole numbers is infinite. The set of all real numbers, which includes every decimal fraction between any two whole numbers, is also infinite, but it is a strictly larger infinity than the whole numbers. There is no way to match up every real number with a whole number without leaving infinitely many real numbers unmatched. Cantor called these different sizes of infinity cardinal numbers, and he showed that the hierarchy of infinities extends without limit, each one larger than the last, in a tower of mathematical abstraction that reaches beyond anything that can be physically instantiated. For cosmology, the relevant question is simpler, but no less profound. Is physical space infinite? Does it extend without limit in every direction? And if so, what does that mean for the distribution of matter within it, for the possibility of repetition, and for the question of edges? In a genuinely infinite flat universe, space extends forever in every direction. There is no center, no preferred location, no point that is special compared to any other. Matter is distributed throughout this infinite space, and on the larger scales, that distribution is roughly uniform. This creates a remarkable consequence that is rarely discussed outside of cosmology, but that follows directly from the mathematics of infinite space and finite probability. If space is infinite, and if matter is distributed throughout it with any finite average density, then every possible arrangement of matter must occur somewhere. Not just arrangements similar to the ones we observe, but exact duplicates. The observable universe, with every galaxy, every star, every planet, every person, every thought, every moment must be repeated infinitely many times throughout the infinite expanse of space. The nearest exact copy of our observable universe, calculated from the statistics of quantum states and the volume of space needed to exhaust all possible configurations, would be approximately 10 to the power of 10 to the power of 118 meters away. That number is so large that it cannot be meaningfully compared to any physical scale. But in an infinite universe, it is a finite distance, and the copy is therefore, in a mathematical sense, out there. This conclusion is not mysticism. It is arithmetic. If you have infinitely many regions of space, each of finite volume, and each region's physical state is drawn from a finite set of possible configurations determined by quantum mechanics, then every configuration must repeat. It is the same logic that guarantees that if you shuffle an infinite deck of cards, every possible ordering of any finite subsequence will appear infinitely many times. The universe, if infinite, is in this sense deeply repetitive at scales far beyond our observational reach, even though locally, within our observable horizon, it appears unique. Whether this kind of repetition is physically meaningful or merely mathematically inevitable is a question that touches on the philosophy of physics. If a copy of our observable universe exists at a distance of 10 to the power of 10 to the power of 118 meters, and if that copy can never interact with us in any way, does it have physical reality in any meaningful sense? Different physicists answer this differently, and the disagreement reflects genuine uncertainty about what it means for something to be real in a scientific framework. Setting aside the question of copies and repetitions, the concept of an infinite universe creates a different kind of challenge for the edge question. An infinite universe, by definition, has no edge. There is no point at which space stops. There is no boundary beyond which something different begins. The question of what lies beyond the edge of an infinite universe is not a question that can be answered, not because the answer is hidden, but because the question is malformed. An infinite universe has no beyond. It simply continues. This is conceptually satisfying in one sense and deeply unsatisfying in another. It is satisfying because it resolves the edge question cleanly. There is no edge. There is no beyond. Space goes on. But it is unsatisfying because infinity is not a physical state that can be confirmed by any observation. We can observe that the universe is very large. We can observe that it appears flat. We can observe that there is no detectable curvature or topology signal within our observable region. None of these observations can confirm that space is truly infinite rather than merely very large. The difference between an infinite universe and one that is merely 10 times larger than our observable horizon is, from our vantage point, completely undetectable. This is where topology re-enters the conversation in a deeper way than we touched on in the chapter on the shape of space. Topology is the branch of mathematics concerned with the global properties of spaces, the properties that remain unchanged under continuous deformation. A coffee cup and a donut are topologically equivalent because each has exactly one hole, and you can deform one into the other without tearing or gluing. A sphere and a flat plane are topologically distinct because no continuous deformation can convert one into the other. For the universe, topological questions ask about the global connectivity of space. Is space simply connected, meaning that any loop drawn in space can be continuously shrunk to a point? Or is it multiply connected, meaning that some loops cannot be shrunk to a point because they wrap around a topological feature of the space? a simply connected flat universe is infinite. A multiplied connected flat universe can be finite because the space wraps around on itself in one or more directions, creating a closed structure without any edge. The simplest multiply connected flat space in 3 dimensions is the 3 torus, which we mentioned briefly earlier. In a 3 torus, space wraps around in all 3 directions. Traveling far enough in any direction brings you back to your starting point, just as walking in a straight line on the surface of the Earth eventually returns you to where you began. A 3 torus is finite in volume but has no boundary. It is a closed space without an edge. Other topologies are possible. Space could wrap around in only 1 or 2 directions, creating a structure analogous to a cylinder or a flat torus. Space could have more exotic connectivity involving reflections or rotations, creating what topologists call non-orientable spaces. In a non-orientable universe, traveling far enough in a particular direction might return you to your starting point as a mirror image of yourself, left and right exchanged, a consequence of the particular way the space wraps around itself. These are not arbitrary mathematical fantasies. They are genuine physical possibilities that follow from the mathematics of general relativity, and that, in principle, leave observable signatures. As we discussed earlier, a universe with a compact topology would show matched circles in the cosmic microwave background, pairs of circles showing identical fluctuation patterns because they represent the same physical region of early space seen from 2 different directions. The absence of detected matched circles places constraints on the minimum size of any topological repetition scale, pushing it beyond our observable horizon. But it does not rule out convex topologies entirely. There is a deeper question lurking beneath all of this, one that topology and geometry together cannot fully answer. It is the question of why space has the extent it has. If the universe is infinite, why is it infinite rather than finite? If it is finite, what determines its size? These questions may not have answers within physics as currently formulated. The size and topology of the universe may be initial conditions, features of the universe that are given rather than derived, facts about the particular universe we inhabit, rather than consequences of any more fundamental principle. Some approaches to quantum cosmology, the attempt to apply quantum mechanics to the universe as a whole, suggest that the universe might have arisen from a quantum fluctuation, a spontaneous emergence from nothing governed by the probabilistic rules of quantum mechanics. In such frameworks, different universes might arise with different geometries and topologies and sizes, and the question of why our universe has the properties it has might be answered, at least in principle, by the probability distribution over possible universes implied by the quantum cosmological framework. But these ideas remain deeply speculative, and the mathematics involved pushes against the limits of what current theory can reliably calculate. What topology and infinity together suggest, when held alongside everything else we have explored, is that the edge question may not have a single clean answer. It may have different answers depending on which aspect of the question we are asking. Within our observable horizon, there is no edge. The universe extends in every direction to the limit of our observational reach, and nothing within that reach suggests an approaching boundary. Beyond our horizon, the universe continues, in a form we cannot directly observe, for an extent we cannot directly measure. Whether that extent is finite or infinite, whether it wraps around on itself or extends without limit, whether it contains repetitions of our own observable region or genuinely novel configurations of matter and space, are questions that sit at the very frontier of what physics can currently address. And there is something important in that frontier. Science does not require that every question be answerable. It requires only that questions be asked carefully, that evidence be gathered honestly, and that conclusions be proportional to what the evidence actually supports. The universe may be telling us, through the very structure of the horizon problem, that some of its deepest properties lie permanently beyond the reach of empirical confirmation. That is not a comfortable conclusion, but it is an honest one. Infinity, in the end, is not something we can see. It is something we can reason toward from the inside of a finite observable sphere, using mathematics and logic and the careful extrapolation of physical law. Whether that reasoning correctly describes the actual universe, or whether the actual universe is something our mathematics has not yet learned to describe, remains beautifully open. In the next chapter, we will bring these threads together in a quieter key, reflecting on what it means to be a thinking, observing presence in a universe of this kind, one that extends beyond our reach in every direction, that may be infinite or finite, edged or edgeless, singular or one of many. It is a chapter for sitting with the questions rather than resolving them, and it is perhaps the most fitting way to approach the end of our exploration. Rest here for a moment. Infinity is not a frightening concept when held gently. It is simply the possibility that there is always more, that beyond every horizon another horizon waits, that the universe has room for everything we can imagine and vastly more that we cannot. That is, in its own quiet way, a deeply reassuring thought. Chapter 8. Living at the edge of what we know. There is a particular quality to the kind of knowledge we have been building throughout this exploration. It is not the knowledge of certainty. It is not the knowledge of a problem solved and filed away. It is something more like the knowledge of a horizon, a clear view up to a certain point, and beyond that point, an honest acknowledgement that the view ends. We have traced the boundaries of what we can observe, explored the geometry and topology of space, reasoned about what might lie beyond our cosmic horizon, and sat with the possibility that some of the deepest questions about the universe may never yield to direct observation. Now, in this second to last chapter, it feels right to step back from the specific scientific content and consider what all of this means for us as the beings asking the questions. We are, as far as we know, the only part of the observable universe that wonders about the observable universe. That is a remarkable fact, and it deserves more than a passing acknowledgement. The matter that makes up our bodies was forged in the cores of stars that lived and died before our sun was born. The carbon in our cells, the oxygen in our lungs, the iron in our blood, all of it was assembled through nuclear fusion in stellar interiors and scattered through space by stellar explosions before finding its way, over billions of years, into the molecular clouds that collapsed to form our solar system, our planet, and eventually the extraordinarily complex arrangements of chemistry that we call living things. We are, in the most literal sense, made of the universe, and we have developed, through the slow accumulation of science over centuries, the capacity to look back at the universe and ask where it ends. That loop, from the universe producing us to us studying the universe, is one of the most striking features of the cosmos as we understand it. It did not have to be this way. The universe could have been a place of pure physics, matter and energy interacting according to fixed rules, producing no structures complex enough to reflect on their own origins. The fact that it is not, that it has, in at least one small corner of one ordinary galaxy, given rise to beings capable of mathematics and telescopes and cosmological theory, is something that no physical theory fully explains. It is simply what happened, and it is worth pausing to notice. The history of human attempts to understand the scale and extent of the universe is a history of repeated expansions. Every era has had its model of the cosmos, and every model has turned out to be smaller than the reality. The ancient sky was a sphere of fixed stars. Then it became a solar system embedded in a galaxy of stars. Then the galaxy became one of many. Then the many galaxies were understood to be receding from one another in an expanding space. Then the expansion was found to be accelerating. Then the total universe was understood to be vastly larger than anything we can observe, possibly infinite, possibly one of many universes in an inflationary multiverse. At each step, the universe grew, and the human observer shrank relative to it, becoming a smaller and smaller presence in a larger and larger cosmos. And yet something curious happens in the wake of that shrinking. Rather than making human existence feel less significant, the expanding scale of the cosmos tends, for many people, to produce the opposite effect. There is a kind of wonder that comes from understanding how large and old the universe is, a wonder that is not diminishing but enlarging. To know that you are a temporary arrangement of atoms in an expanding universe 13.8 billion years old, orbiting an unremarkable star in an ordinary galaxy in a supercluster that is itself a minor feature of the cosmic web, and to be able to know that, to comprehend it, to feel something in response to it, is not a small thing. It is, in its own way, as remarkable as the universe itself. This is not a mystical claim. It is an observation about the nature of scientific understanding and its effect on those who engage with it seriously. The physicist Richard Feynman wrote about the way scientific knowledge adds to, rather than subtracts, from the beauty of a flower. Knowing the chemistry of a petal, the physics of its color, the evolutionary history of its form, does not make the flower less beautiful. It makes it more. The same is true of the universe. Knowing that the night sky is a cross-section through a cosmic web of galaxies, that the faint smear of the Milky Way is our edge-on view of a disk of 400 billion stars, that the darkness between stars is not empty, but filled with gas and dust, and the faint glow of ancient light, does not diminish the experience of standing under a dark sky. It deepens it. The question we have been pursuing throughout this exploration, whether the universe has an edge, is one that sits at the precise intersection of the answerable and the unanswerable. Within our observable region, the answer is clearly no. There is no edge we can see, no boundary we are approaching, no wall at the limit of our telescopes beyond which space simply stops. The observable universe is a sphere of space 93 billion light-years across, filled with matter and structure and ancient light, and it gives no indication of approaching any kind of terminus. Beyond our observable region, the answer becomes uncertain in a deep and perhaps permanent way. The total universe may be infinite, extending without limit in every direction, in which case the question of an edge is simply inapplicable. Or it may be finite, curving back on itself in a topology that closes space without creating a boundary, in which case the question of an edge is again inapplicable, though for a different reason. Or it may be something else entirely, something our current mathematics has not yet learned to describe, in which case the question may need to be reformulated before it can be answered. What is striking about all three possibilities is that none of them involves the kind of edge that the naive imagination tends to picture. A wall in space beyond which there is nothing. a place where the universe stops and emptiness begins. That image, compelling as it is, does not appear to correspond to any physically meaningful possibility. Space does not end the way a room ends. It either continues without limit, or it closes on itself without creating a boundary, or it opens onto something that is not space in any familiar sense. The edge, if it exists, is not a wall. It is something stranger and more subtle. There is a philosophical tradition, stretching back through centuries of human thought, of finding meaning in limits. The Stoic philosophers of ancient Rome and Greece counseled attention to the limits of what is within our control, arguing that wisdom lies in accepting what cannot be changed and directing effort toward what can. The Japanese aesthetic concept of ma, sometimes translated as negative space or interval, finds beauty and meaning in emptiness and absence as much as in presence and form. The Buddhist tradition speaks of the value of sitting with uncertainty, of not forcing resolution onto questions that are genuinely open, of finding peace in the act of inquiry itself, rather than only in its conclusions. These traditions were not developed with cosmology in mind, but they map onto the situation of the cosmologist with surprising precision. The universe presents us with questions we cannot fully answer. The extent of space beyond our horizon is genuinely unknown. The topology of the total universe is genuinely undetermined. Whether the multiverse is real, whether inflation is eternal, whether the cosmological constant is truly constant or will change over time, these are open questions at the frontier of human knowledge, and they may remain open for a very long time, perhaps permanently. The appropriate response to that situation is not frustration or disappointment. It is something closer to the attitude of the dedicated explorer, someone who finds value in the journey itself, who understands that the frontier is not an obstacle but the most interesting place to be. The history of science is a history of frontiers being pushed back, of questions that seemed unanswerable, yielding to new instruments and new ideas. There is every reason to expect that future observations, future theoretical developments, and future generations of scientists will learn things about the universe that we cannot currently anticipate. The cosmic microwave background, which has already told us so much, will be mapped with greater precision. Gravitational wave astronomy, still in its early years, may reveal new information about the structure of spacetime at cosmic scales. Surveys of the large-scale distribution of matter will grow more detailed and extend to greater distances. The picture will sharpen, even if it never becomes fully complete. And there is something to be said for the questions that remain permanently open, the ones that may never yield to direct observation, no matter how sophisticated our instruments become. These questions are not failures of science. They are markers of the limits of the knowable, and they have their own kind of value. They remind us that the universe is larger than our theories, that reality exceeds our models, that there is always more beyond the edge of what we currently understand. That reminder is, in its own way, a gift. We are beings of finite lifespan, finite sensory reach, finite cognitive capacity, living in a universe of possibly infinite extent, definitely enormous age, and extraordinary complexity. We have developed, through the collective effort of thousands of generations of curious minds, the tools to understand a remarkable fraction of what surrounds us. We know the composition of stars from their light. We know the age of the universe from the expansion of space. We know the geometry of spacetime from the behavior of matter within it. We know the structure of the early universe from the faint microwave glow that reaches us from its first moments of transparency. These are not small achievements. They are among the greatest things our species has ever done. And yet we stand at the edge of our observable sphere, looking out at a cosmic horizon beyond which we cannot see, knowing that the universe continues in directions and forms we cannot directly access, asking questions whose answers may lie permanently out of reach. That is the position of the honest scientist, and it is a position worth inhabiting with grace. The edge of what we know is not a stopping point. It is an invitation. It is the place where the next question begins, where the next generation of instruments and ideas will find their purpose, where the universe continues to offer itself to our curiosity without ever fully yielding to it. There is something deeply satisfying about that arrangement, even in its incompleteness, perhaps especially in its incompleteness. As we move into our final chapter, we will let these reflections settle into something quieter still, a closing meditation on the universe as a place to inhabit thoughtfully, on the questions that accompany us through life without demanding resolution, and on the particular kind of peace that comes from understanding how much there is still to understand. For now, rest with this. You are made of the universe. You are part of the thing you are wondering about. And the wondering itself, the quiet, patient, open-ended inquiry into the nature of the space you inhabit, is one of the most distinctly human things there is. Chapter 9. The Universe as a Place of Permanent Mystery. There is a phrase that appears in various forms across the history of science, attributed to different thinkers in different eras, but expressing a sentiment that seems to arise naturally from deep engagement with the natural world. The more we know, the more we realize how much we do not know. It is easy to dismiss this as a platitude, the kind of thing said at the end of lectures to sound appropriately humble. But when examined in the context of cosmology, it turns out to be not a platitude at all. It is a precise and measurable description of how scientific knowledge actually grows. When our picture of the universe was small, our catalogue of unknowns was also small. The ancient sky presented a finite set of questions. Why do the planets move the way they do? What are the stars made of? How far away is the moon? These were difficult questions for their time, but they were bounded. The universe was conceived as a manageable place, its mysteries proportional to its apparent size. As the universe expanded in our understanding, the questions expanded with it, and they expanded faster than the answers. Every major discovery in the history of cosmology has generated more new questions than it resolved. Hubble's discovery of galactic recession answered the question of whether the universe was static, and immediately raised the question of what had set it in motion and what had existed before. The discovery of the cosmic microwave background confirmed the Big Bang model and immediately raised the question of what had caused the extraordinary smoothness and uniformity of the early universe, a smoothness that the standard model could not explain without additional machinery. Inflation was proposed to explain that smoothness, and immediately raised the question of what had caused inflation, what the inflaton field was made of, and whether inflation was still occurring somewhere beyond our horizon. The discovery of accelerating expansion answered the question of the universe's long-term fate in broad strokes, and immediately raised the question of what dark energy is, why it has the value it has, and whether it will remain constant or change over time. This pattern is not a sign of scientific failure. It is a sign of scientific success. Each answer reveals a deeper layer of the question, a more fundamental level at which our understanding is incomplete. The universe is not a crossword puzzle with a finite number of squares. It is more like a landscape that reveals new terrain in every direction as you climb higher, each summit offering a view of further mountains rather than a final edge. The question of whether the universe has an edge is, in this sense, a perfect example of the kind of question that science can partially answer and permanently deepen. We can say with confidence that the observable universe has no edge within our view. We can say with reasonable confidence that space, in its large-scale geometry, shows no curvature that would imply a nearby boundary. We can say with theoretical grounding that the universe beyond our horizon is likely vast, possibly infinite, and organized according to the same physical laws that govern our observable region. And we can say honestly that the questions of the total extent of space, the global topology of the universe, and the reality or unreality of regions beyond our horizon are questions that current physics cannot definitively answer and may never be able to answer through direct observation. That honest accounting is not a diminishment of what science has achieved. It is rather a demonstration of science's greatest strength, its willingness to distinguish between what is known and what is not, to hold uncertainty without collapsing it prematurely into false confidence, and to continue asking questions even when the answers are not forthcoming. There is a related quality that the best scientists tend to share, one that is difficult to teach but easy to recognize. It is a genuine comfort with not knowing, not a passive resignation to ignorance, but an active and energized relationship with open questions, a capacity to find the unanswered question as interesting as, or more interesting than, the answered one. The physicist Niels Bohr reportedly said that an expert is someone who has made all the mistakes that can be made in a very narrow field. There is something in that formulation that applies to the cosmological frontier as well. The cosmologist working at the edge of the observable universe is not someone who has run out of things to discover. They are someone who has explored enough of the known to understand clearly where the unknown begins. The unknown, in the case of the universe's extent and possible edge, is genuinely profound. It is not the ordinary unknown of a calculation not yet performed, or an observation not yet made with available technology. It is, in some of its aspects, the unknown of the in principle inaccessible, the region beyond the cosmic horizon that no future telescope, however sophisticated, can ever reach. That kind of unknown is philosophically different from the ordinary scientific frontier, and it raises questions that go beyond the methodology of physics into something closer to the philosophy of knowledge itself. What does it mean to have a scientific theory that makes predictions about regions of reality that can never be observed? This question is not new to cosmology. It arises in quantum mechanics, where the many worlds interpretation posits the existence of branching parallel realities that can never interact with our own. It arises in string theory, which operates in mathematical spaces of 10 or 11 dimensions, of which we can directly observe only 4. It arises whenever theoretical physics ventures into territory where mathematical consistency outpaces observational confirmation. The universe beyond our horizon is perhaps the most physically concrete version of this problem, because it is not a mathematical abstraction, but an actual region of space, governed by the same physical laws as everything we observe, simply too far away to see. One response to this challenge is to insist that science must confine itself to the observable, that any claim about regions beyond the horizon is metaphysics rather than physics, and that the business of science is to describe what can in principle be measured and nothing more. This is a coherent position, and it has serious defenders. It has the virtue of keeping science tethered to its empirical foundations and preventing the kind of speculative excess that can occur when mathematical elegance is mistaken for physical truth. Another response is to argue that the distinction between observable and unobservable is not a fundamental divide, but a practical and temporary one, and that a theory which correctly predicts everything within our observable region has earned some degree of credibility for its predictions about the unobservable regions as well. On this view, the multiverse is not beyond the pale of science simply because it cannot be directly observed. It is a theoretical inference from a framework that makes correct observable predictions, and it deserves to be taken seriously as a physical possibility, even if it cannot be confirmed in the way that a laboratory experiment can be confirmed. Both positions have merit, and the tension between them is productive rather than paralyzing. It keeps scientists honest about the limits of their claims while preserving the freedom to reason beyond those limits when the reasoning is well grounded. The universe does not care about the philosophy of science. It simply is what it is. Our job is to describe it as accurately as we can, to acknowledge clearly where our descriptions become uncertain, and to continue pressing forward with both humility and ambition. What the universe has shown us, through every expansion of our understanding, is that it is stranger and richer than we expected. The discovery that space itself expands was strange. The discovery that the expansion is accelerating was stranger still. The possibility that our observable universe is one bubble in an eternally inflating foam of universes, each with its own physical constants, is stranger than almost anything our ancestors could have imagined. And yet, each of these strange discoveries has followed from careful observation and rigorous mathematics, from the ordinary tools of science applied with patience and precision, to the extraordinary subject matter of the cosmos. There is a particular kind of peace that comes from accepting that the universe is larger than our understanding, and that this gap between universe and understanding is not a temporary condition to be overcome, but a permanent feature of the relationship between a finite mind and an infinite, or at least vastly larger, reality. It is the peace of the naturalist who knows that no matter how long they study a particular ecosystem, the ecosystem will always contain more than they have catalogued. It is the peace of the mathematician who knows that no axiomatic system can capture all mathematical truth. It is the peace of the philosopher who knows that every answer opens onto further questions and has learned to find that opening beautiful rather than frustrating. The universe, in its vastness and its mystery, invites exactly that kind of peace. It does not demand that we resolve every question before we can appreciate it. It does not require complete understanding before it offers wonder. It is available to the specialist and the amateur alike, to the professional cosmologist and to the person lying quietly in the dark, letting the ideas drift through their mind like light through deep space, slow and steady, and carrying information from an unimaginable distance. We have come a long way in this exploration, from the basic question of what we mean by the universe, through the structure of the observable cosmos and the large-scale architecture of the cosmic web, through the geometry and topology of space and the dynamics of an accelerating expansion, to the frontier of what lies beyond our horizon and what physics can say about the permanently unobservable. In our final chapter, we will bring all of these threads gently together, not to resolve them into a tidy conclusion, but to let them rest alongside one another in the way that a long and satisfying journey deserves to end. Quietly, without hurry, with appreciation for the distance traveled and the questions that remain open ahead. Chapter 10. the long quiet of space. There is a particular quality to the silence that follows a long journey. Not the silence of emptiness, but the silence of arrival, of having travelled far enough that the distance itself has become part of you, carried in the body as a kind of weight that is not unpleasant, a settled feeling of having moved through something large and come out the other side changed in ways that are difficult to name precisely, but easy to recognize. That is the quality of silence we are reaching for in this final chapter. Not the silence of unanswered questions left behind, but the silence of questions held openly, travelled with, turned over slowly in the mind, until they have become familiar companions, rather than unsettling strangers. We began this exploration with a question so simple, it could be written in 7 words. Does the universe have an edge? We ended not with a 7-word answer, because no such answer exists, but with something richer and perhaps more valuable than a simple answer. We end with a clearer sense of what the question actually means, of the different layers it contains, of what physics can say, and where physics reaches its current limits, and of what it feels like to be a thinking being in a universe that exceeds our capacity to fully know it. Let us take a slow walk back through the ideas we have covered, not as a summary in the conventional sense, but as a kind of quiet revisiting, the way you might walk back through a landscape you have just crossed, pausing at the places that meant the most, letting the light fall differently on the things you saw the first time in a different direction. We began by distinguishing between the observable universe and the total universe. That distinction turned out to be one of the most important clarifications in all of modern cosmology, because the question of edges means something entirely different, depending on which universe you are asking about. The observable universe has a boundary, the cosmic horizon, beyond which no light has yet reached us. But that boundary is not an edge of space. It is an edge of our knowledge, a limit imposed by the finite age of the universe and the finite speed of light. It is a practical horizon, not a physical wall. The total universe, whatever its true extent, continues beyond that horizon in ways we can reason about, but not directly observe. We then looked at the observable universe itself, at its true size, which is far larger than intuition initially suggests. 93 billion light-years across, not 13.8, because the space through which ancient light has travelled has been expanding throughout the journey. We looked at the cosmic microwave background, the oldest light in the universe, a faint microwave glow that fills the sky uniformly and represents the last moment of the universe's opacity, the instant when matter and radiation decoupled and space became transparent for the first time. That ancient light is the farthest thing we can see, a screen of early universe conditions beyond which our telescopes cannot penetrate. We moved then from the edge of our vision to the structure of what lies within it, the cosmic web of filaments and voids and clusters that organizes matter across the larger scales. We saw that the universe is not smooth and uniform at intermediate scales, but textured with the cumulative record of 13 billion years of gravitational evolution. Filaments stretching across hundreds of millions of light years. Voids nearly as wide, nearly empty, slowly growing emptier as matter drains outward toward the denser surrounding structures. Clusters at the intersections of filaments, the most massive gravitationally bound objects in existence. And underlying all of it, a statistical homogeneity that emerges when you average over scales large enough to contain many filaments and many voids, a uniformity that supports the cosmological principle and the idea that the universe has no preferred center and no preferred direction. We then turn to the shape of space itself, to the question of geometry and what it implies about finite or infinite extent. We found that the universe appears flat, consistent with Euclidean geometry on the largest observable scales, with a measured density within about 1% of the critical density that separates a positively curved from a negatively curved cosmos. That flatness is consistent with an infinite universe, but it is also consistent with a finite universe whose topology closes space on scales larger than our horizon. The geometry tells us the local rules of space. The topology, which remains undetermined, tells us the global structure, how space is connected, whether it wraps around on itself, whether there is a finite volume of space or a truly limitless expanse. We explored expansion and the role of dark energy, the mysterious component that accounts for approximately 68% of the total energy budget of the universe and drives the accelerating separation of distant galaxies. We saw that the expansion of the universe is not the movement of matter through space, but the stretching of space itself, and that the acceleration of that stretching, driven by dark energy, is slowly reducing the effective size of our connected cosmos, carrying galaxies beyond our event horizon one by one over timescales of billions of years. We live at a fortunate moment in cosmic history, early enough to see an extraordinary richness of structure, late enough to have the tools to interpret what we see. We ventured beyond the observable horizon into the territory of inference and theory. Considering what physics can say about the regions of space we will never directly observe. We found that the most conservative and most probable inference is that those regions contain more of the same, more galaxies, more filaments, more voids, arranged according to the same physical laws that govern our observable sphere. We considered inflation, the theoretical framework that explains the smoothness and flatness of the observable universe through a period of extraordinarily rapid early expansion. And we noted that many inflationary models predict a vast or infinite universe well beyond our horizon, possibly organized into a multiverse of bubble regions, each with their own physical character. We held those ideas with appropriate tentativeness, recognizing their theoretical motivation, while acknowledging that direct confirmation may be permanently beyond our reach. We thought carefully about infinity and topology, about what it means for space to be truly infinite rather than merely very large, about the mathematical possibility of a finite but boundless universe whose space wraps around on itself without creating any edge or boundary. We considered the way topology and geometry together shape the possible structures a universe can have, and we found that current observations can constrain but not determine the global topology of space, leaving the question of finite versus infinite genuinely open. And we spent time with the human dimension of all of this, with what it means to be a thinking, wondering presence in a universe of this scale and this mystery. We noted that the expanding scientific picture of the cosmos has not diminished the experience of being alive within it, but has, for many people, deepened it. We considered the particular value of questions that remain permanently open, the way they keep the mind alive and attentive, the way they resist the closure that can sometimes make knowledge feel like an ending rather than a beginning. All of these ideas, held together, constitute our best current answer to the question we began with. Does the universe have an edge? Within our observable region, no. Beyond it, we do not know, and may never know with certainty. The question itself, examined carefully, reveals itself to be not one question but many, each requiring its own kind of answer, each opening onto further questions that invite further exploration. There is something fitting about ending a long exploration with open questions, rather than closed conclusions. The universe itself seems to be structured that way, each layer of understanding revealing a deeper layer of mystery, each answer carrying within it the seeds of the next question. Science, at its best, mirrors that structure. It does not march toward a final, complete description of reality and then stop. It moves continuously forward, each generation inheriting a richer set of questions than the one before, each discovery expanding the frontier rather than shrinking it. For the person lying quietly in the dark, listening to these ideas drift past like slow music, the open questions are perhaps the most restful part of all. A closed question demands an answer, pulls the mind toward resolution, creates a kind of tension that is incompatible with rest. An open question, held gently, without the expectation of immediate resolution, becomes something else entirely. It becomes a companion, a presence that asks nothing of you, except that you remain curious, that you stay open to the possibility that the universe is larger and stranger than your current understanding, that you make peace with not knowing while continuing to wonder. The universe is approximately 13.8 billion years old. It has been expanding since its beginning, growing larger in every direction, cooling as it expands, its matter gathering into stars and galaxies and the cosmic web, its space stretching under the quiet influence of dark energy, its oldest light still traveling toward the edges of whatever extent it truly has. In all of that time, in all of that space, the questions we have been asking tonight have been forming slowly, waiting for the particular arrangement of matter and chemistry and culture that would eventually produce beings capable of formulating them. We are that arrangement. We are the universe's way of asking about itself. That is not a small thing to carry into sleep. It is, in fact, one of the largest things there is, and it requires no resolution, no final answer, no conclusion that ties everything together neatly before the mind can rest. The questions can come with you into sleep, can drift alongside the fading awareness of your body and your surroundings, can be there when you wake, unchanged and waiting, patient as the cosmos that generated them. The stars outside, if you could see them, are doing what they have always done, burning quietly at distances that dwarf every human scale of measurement, sending their light outward in every direction, some of it falling on planets, some on empty space, some eventually reaching the instruments of patient astronomers who will spend their lives learning what that light has to say. The galaxies are moving apart, slowly, carried by the expansion of space, unaware of one another in any meaningful sense. Each a city of billions of suns drifting on the currents of a universe too large for any of them to know its own extent. And here, in whatever quiet place you have made for yourself tonight, a small arrangement of atoms that somehow learn to ask where it all ends is settling into rest. The question remains open. The universe remains vast. The edge, if it exists, is far beyond anything we can reach, and that is, in its own particular way, exactly as it should be.